All right, guys. So welcome to the neural networks workshop. Um, this is probably going to be, one of the longer notebooks because it's just like, getting familiar with PyTorch, but hopefully it'll be rewarding because this will be like, when you really start actually building neural networks and understanding how all of the other models work. So, in some sense, this workshop is like the basis for everything in deep learning. But I actually don't think it's that complex. So, I guess yeah. So we can kind of start this out by asking, kind of like what did we do last week? Well, last week we did linear regression, right? And so linear regression was just basically a linear sum of your input features. So like before we had the x's, so x1 to x, n were just like the inputs, and the weights w, scaled those inputs, and then you summed all of them. So it's just linear functions, right? So we can take this linear function, and instead of representing it by this equation, we can try and represent it by a graph. Uh, so this is what's called like a perceptron, essentially. So rather than representing it by this equation here, you can simply put all of these uh, variables on a graph, and they'll represent different things. So all of the x1s, which are the inputs, can represent these nodes, which are drawn in blue, and all of the weights w can represent edges in the graph. And then when you have edges going into a node, they all sum up. So inside of these nodes, there's normally some sum operation, and then the output of this would be y, right? Pretty straightforward. So this is literally the same thing as linear regression. There's no difference. Well, what relevance does this have? Well, we'll get to it in a bit, I guess. So can we do this for classification? Yeah, you can do this for classification. So how would we do logistic regression using this type of graph? Well, we take the same model we had before. This right here would be, the y hat for linear regression. And the only difference between, logistic regression and linear regression, as we saw last week, is that you add this sigmoid function at the end. And so basically here, this would be not w transpose x. This would be like the z, or the input from the last node. And then the output here would be the guessed class, or the probability of being in class 1. So now we can use this to represent logistic regression as well and do classification problems. Okay, so now in order to make our networks deep, we're basically going to do the same thing that we just did by kind of taking our really simple classifiers and putting them on graphs, but with a few caveats. So one question is like, what prevented our models from working very well on all data before? And the answer to this is like they were linear, right? So because the models were linear, they were inherently restricted in what they could represent. So for example, here's some linear data, and this is maybe the most simple example. This is some linear data, and you don't include the bias term, right? So you're trying to fit y equals w1 x1 instead of y equals w1 x1 plus w2. And that W2 is the bias term, right? And so that would allow your decision boundary, or your regression line, to shift towards where the data is. But if you don't have that bias term, you can't represent this data well. And so there's kind of this mismatch that we saw where, if your data is not linear, your linear models don't work well. But the caveat to this is that we were able to use additional features in our data in order to fit these more complex data sets, right? So you probably saw this in the notebook as well, where, there was an example from this where you added the feature, you know, uh, x1 squared plus x2 squared, or something like that, right? And once you added this feature, you were able to fit this using a decision boundary. So the solution is to, design these extra features. But the problem is doing this is, it's really time consuming. It's annoying, and you're a human, so you can't really enumerate all the useful features, and maybe they just get way too complex. And so the solution to this is trying to learn the features instead of just the decision boundary. And this is all neural networks do. Is at the end of a neural network, there's going to be some linear regression, some classification model, but before that, you're just going to learn the input features to that final model. So how do we do this? Well, we take our original linear regression model, which is like here, right? So this could be like lin regression, or it could be logistic regression, something like that. And we're just going to basically perform this, but we're not going to perform this linear regression on the inputs of the data. We're going to perform it on some transformed version of the data, right? And so here's the actual input. And now we, compute some combinations of all of these different input features, and we use that as the input to our new regression at the end. So this is the same as before, where, you have W's or weights along each of the edges, and all of the inputs to a node get summed up. So yeah, you're summing up over here in each of these across all of the different inputs to them. So any questions on anything so far?
Is there like some sort of logic or some sort of understanding as to how we map these like nodes to their edges?
I mean, eventually this would just be a matrix multiplication, but this is just kind of a way of understanding it visually.
So we do all the combinations.
Yeah, so the way you choose, what weights go into which layer is essentially neural network architecture design, right? So this is the simplest version where every node goes to every other node, right?
Right.
But yeah, later you'll realize that that's not the best choice for all types of data. So um, that's basically what you'll study the rest of the semester is how to choose these, the structure of these networks better. Um, So yeah, there's some terminology. Yeah, remember the edges correspond to weights, and the values in the nodes are often referred to as activations. So you could think of each of these nodes as like some neuron, right? And then if the neuron exceeds some threshold, it's activating or it's firing, and so people call these the activations of the network. Although that term kind of gets conflated with something else we'll talk about later. So yeah, remember we also need biases to fit our data. So, you know, this problem from before, you want to make sure that your decision boundary in your neurons doesn't have to go through the origin. So we also add a bias term to our neurons as well. So all of these nodes will also have a bias term in them. Although I'm not going to like draw it out explicitly on the slide because that takes a lot of space. So basically, you want every single node to be able to center itself in some region, or normalize. Um, so you add the bias back in. And so, yeah, you can continue doing this as long as you want, and you can make more and more neural network layers. So before we just had one layer, and you'd call this like a hidden layer. So this would be a neural network with two hidden layers. And what this would be called is like a multi-layer perceptron. So just the simplest thing where you put the linear model on a graph is a perceptron. Now we have multiple of these hidden layers. It's a multi-layer perceptron. But one thing to remember is that we haven't actually done anything yet. So I've kind of shown you guys all these images of neural networks without telling you that none of them would actually work. They would all still just do linear regression. And that's because there's one secret thing that you need to do in order to get neural networks to learn good features. So far, we've represented each of these edges with a weight and each of these nodes with a sum, right? So that means essentially each one of these nodes is given as a linear combination of the previous nodes, right? So this first row is just linear combinations, right? And then now this second row is what? It's just linear combinations. Same thing. And now this last row, this last node, it's also going to be a linear combination. And so as you can see, everything is a linear combination. And so if you were to actually write out all of this, this multiplication and this adding, in the end, you could derive an expression that, says that y is equal to some, w hat 1 times x1, w2, or plus, w hat 2, x2. The idea is that because everything here is still linear, the output is still going to have a linear representation. And so this actually hasn't given us any more power than our linear regression model has yet. Does this make sense? It's kind of a subtle point. But because all of these features, all of these sums so far are linear sums, nothing has actually changed. So we need to get rid of the linear nature of these neural networks in order to make them fit more complex things, right? And so if you're not maybe convinced of this yet, I would encourage you to go back and don't do it for, this two-layer network. You can draw out a really small network, of like something like this. And you can do all of the math, and you'll see that if you don't add something nonlinear in there, your output y at the very end is just going to be a linear sum of the input. So, okay, clearly we need to make things nonlinear. Well, how do we do that? The basic idea is we add what are called activation functions, or nonlinearities to our data. So to force our models to learn something nonlinear, we literally just apply a nonlinear function at the end of every single one of these nodes, right? So before it was just the sum of its inputs. Now it's the sum of its inputs, and then you take that sum and you apply a nonlinearity to it. And so there are a bunch of different ways that this happens because there are tons of different activation functions. The original motivation for this, if you want to like go back to it, is kind of that people said, oh, well, neurons are kind of a little binary. They fire 0, 1. So we should apply a sigmoid function at every single one of the neurons. And then much later, people realized that, the sigmoid function actually isn't really the best function to use. And so there are a bunch of other different activation functions that people use to get different characteristics from their network. But essentially, yeah, you apply these nonlinearities, makes your network nonlinear. Now you can represent much more things. So yeah, here's some examples of activation functions that are used. I'd say the most commonly used are the tanh and the ReLU now, depending on your application. Computer vision always uses ReLUs. Sometimes, if you do unsupervised learning, you'll use leaky ReLUs. But yeah, basically all of these are different ways of injecting nonlinearities into your system. This is Praveen's meme.
Wait, for the expressions that were on this last page, is x like the weighted sum
Yeah,
already?
X here would be the weighted sum.
Okay,
Yeah, sorry. I pulled this from something else. So I think this is just an image, so I couldn't change all the notation.
okay.
Yeah. So, okay, I guess this is something that I probably should have taken out. But, if you're interested in learning more about kind of the theoretical math, there's this thing called the universal approximation theorem that says you can actually represent any function you can think of by a single layer neural network if you have enough nodes in it. Or, sorry, like a neural network with a single hidden layer can represent anything that you want. You just need to have, infinite number of nodes. So yeah, but anyway, so we've improved our model by adding these activation functions. Now our output is nonlinear with respect to the input, so we can learn a bunch of different things. And now, we can, if you say, okay, well, maybe my model's not accurate enough, we can add more and more layers. More layers means more weights to optimize. Your whole neural network gets slower, and it gets maybe harder to learn. So how do we pick these weights? Well, you use gradient descent, as always. It's the same exact algorithm that we showed last week. Except now you're doing it with respect to each of the individual nodes in the network, or each of the individual weights. And so you have to back propagate multiple steps. So you can take a gradient going this way to get the gradient of the loss with respect to the first weight. Then you can, continue going backwards through all of the different connections in the network and get all of the other gradients and use that to update the weights. And so a common way to think about neural networks is via matrix multiplication, and this is actually how it's implemented in your computer. And the nice thing about this is, you can use things from matrix calculus in order to calculate the derivatives. But the basic idea is that if you think about it, here's a representation of my network. A represents, the activations at that layer. W is a matrix that represents the weights. And so this row of the matrix here corresponds to everything in red in this top image. And as you can see, if I multiply this weight matrix W by the activations at layer L minus 1, I can basically get a sum of all of the first nodes on this side with respect to like the first row of the weights. So here I multiply this way across and this way down, and this gives me the sum that belongs in this position there. And so basically you can just know, it's not important that you actually know this in practice because you'll never have to write neural networks as matrix multiplication, but it's good to know that this is actually what's happening. And so when you want to represent the entire neural network, you can basically nest a bunch of these. So if I were to write out, all the neural networks that I've showed in the previous slides in a mathematical expression, this is what it would look like, where f is some activation function, right? XW is that matrix multiplication from the last slide, and B is a vector of biases. And so now this is what the entire expression looks like. And you calculus savants should know that if you see some nested function that looks like this, all you can do is apply the chain rule and you can get the derivatives, right? So how do you actually run gradient descent? Well, the idea is, you pass forward through the network and basically you'll compute the values as you go. And then when you want to get the derivatives, you can basically use the chain rule. So here I'm taking the loss with respect to the output z, and then as I move backwards, I can take the loss with respect to each of these other components here by applying the chain rule. So this would be the loss with respect to input x is the derivative of the loss here with respect to z multiplied by the derivative of z with respect to x. And because everything that goes into a node is normally, something simple like a matrix multiplication and an activation function, this is not that complex to do. But your computer handles all of this for you, and Praveen will talk about this a lot more. So yeah, I think what we've shown you guys so far, to just summarize, is dense or fully connected or multi-layer perceptron neural networks. And a few characteristics you should maybe know about these is that they tend to overfit your data. I guess you'll talk about this in like the next workshop. But basically, the idea is you have tons and tons of parameters, and so it's very easy for it to memorize the data, which can be bad. It has tons and tons of these parameters also, as I just said, so it's pretty slow to optimize. And there's some other tips and tricks that people apply in order to make these networks work a little bit better. And yeah, just a reminder, I guess, of kind of what I also showed last week is that we have this idea of a gradient, which is like the reason why we named gradient descent is because it takes gradients, and it's basically just a vector of all the partial derivatives. And so as you can see, we can basically represent all of the steps that we did before for our neural networks by using gradient descent. And so I guess this is just a reminder. I'm not particularly sure what the order of these slides is now. This looks like it's a repeat, Praveen. We already went over this.
Yeah, you can skip some of these.
Yeah.
I probably should have removed them.
Okay. Yeah, so gradient descent, we went over these steps last week, but yeah, you basically find the gradient, you take a small step in its direction, and then you keep going until your loss is optimized. Okay, and now I think this is where Praveen is taking over, right?
Yes, so I'll go ahead and share a screen. Let me navigate to the right slide.
Let me stop.
I had a question about like how do neural networks? You said like they're learning the features also. How is that like? I didn't really see how it worked in the network.
Oh, so the idea is that last layer of the neural network, right? That's just all of the three, one line of neurons leading into one output, right? That's just a linear regression, and that's what we showed at the start. So everything before that is just figuring out what the input to that final regression should be, if that makes sense, right? So essentially,
could you figure out like in the final layer, like what do those features mean?
No. So that's one of the problems of the neural network, right? Is it's learning the features in the neural network, so you can't really figure out what the features are. It will sometimes, there are visualizations of convolutional neural networks and a bunch of other things that kind of try and get at what the networks are learning as the input features. But explainability is a big problem in deep learning in general. It's hard to know what the actual features are and what they represent. You kind of just fit this to your data, and then because you don't know what the features are, it's really important that you test on a test set, and then you can see how well it would actually do on some unseen data. But yeah, basically the entire network up until the last, that very last linear regression or logistic regression or, multi-class classification head is just learning features that input to this final regression.
Okay, sweet. Sounds good. Thanks.
Yeah.
All right, unless there are any other questions, we'll go ahead and start talking about PyTorch now. So the first question is sort of why do we need a dedicated library for deep learning? And the reason is that, when we talk about the chain rule process, how the gradients are computed and how this can be used to update the weights, it's a fairly involved process, right? Especially when you're taking like, derivatives of tensors, and applying, all these different chain rules. It can be pretty involved. And it's really nice to have a library that can sort of just do this for us. So we just, set up our network, do our computes, and it can compute the gradient update weights for us using the chain rule automatically. And so that's really nice. And also being able to optimize all these layers to run on GPUs, because GPUs can be really fast with matrix multiplies. And so if you want to run a large neural network, running it on a GPU can get you a much bigger speed up. But this is not something that, say, NumPy, for instance, does not support using GPUs. So PyTorch basically had to re-implement a lot of NumPy's matrix multiplication, matrix handling, but just make it optimized for GPUs. All right, so let's start by talking about the different machine learning libraries. That these are sort of the three most common ones. There are others out there, but these are probably the most common ones that you'll encounter. So for a lot of classical machine learning, for stuff like decision trees, linear regression, sklearn is pretty commonly used. For deep learning, there's sort of two main ones. There's TensorFlow, which is by Google, and there's sort of this TensorFlow V1 was sort of a very kind of old-fashioned approach in that they sort of said, like, we're going to have you set up your model graphs. You sort of tell TensorFlow exactly what the structure of my model is. Like, okay, I have like this input, and it's going to connect to this layer, and this layer is going to connect to this layer and go to this output. And then you create, like, you actually go like create an instance of this model, and you give it values and you train its weights and stuff. And it was just kind of annoying to use. So then in their version 2 of TensorFlow, they said, all right, we're just going to say, you just like call all your different functions, all your different layers, and we'll figure out what's going on. And PyTorch is from Facebook, and they sort of took that approach from the start. They said, we want to make it easier for people to build these models and train these models. And that's sort of why PyTorch, in my opinion, has sort of a pretty good amount of traction, both in academia and industry, for its ease of use. So before we start, always remember that what I'm going to teach today is sort of just sampling a lot of the capabilities of PyTorch and some basic idea of like how things work and how ideas work. A lot of this is, if you look up how do I do X in PyTorch, or you go to the PyTorch docs and you look for some function that does what you want, that's one of the ways that can be really helpful. And of course, for a lot of specific networks or models that you'll be implementing in your projects, there will often be blogs, Medium articles related to those, right, that might have sample code that you could reference that could be really helpful in figuring out what the best way to implement something is. So documentation is really helpful in these cases. All right, so let's talk about what is a PyTorch network. So in short, PyTorch network is a Python class. You inherit from nn.module, which I'll talk about in a second. And there's basically two main functions that are the most important ones to implement. In the initializer, any sort of layers that have weights. So, we had here, say each of these edges, right, was weights, right? We had a matrix of all these weights. Those are all going to be declared, set up in this initializer. And then in this forward function, basically, PyTorch does some magics that if you create some net and you say call net of X, it will call this forward function with the input X. And so what you do is you sort of run it through the layers, you run it through any activation functions you want, and you return the output. So just to talk a little bit more about that. So module sort of represents abstractly either a neural network or like a single layer in a neural network. So you can sort of compose networks together to create, a bigger neural network. And you inherit from this class when you create your own model. And then there's this parameter. So it basically, basically an nn.parameter contains a tensor, but when you basically add like a variable, you basically say like, okay, self dot, parameter 1 equals this. It will automatically keep track of all the tensors so that you can use them for, updating weights and stuff like that. So the next thing is just another type is this called nn.sequential. So this is one thing where if you want to just run a bunch of layers one after the other, you can just put them in a sequential. So you just pass in a list of the modules and it will just run one after the other. I don't have too much information about this, but you can look up nn.sequential if you're curious. They have some code examples. But anyway, so let's now get into talking about, so that was sort of very high level overview, but let's sort of talk about what are the sort of fundamental data types that are being manipulated in PyTorch. And the first one, the most important one, is the tensor. So just a quick show of hands on the participants tab. Can you put yes if you're familiar with NumPy arrays and no if you're not familiar with NumPy arrays? All right, cool. So it looks like most people are familiar with NumPy arrays. So tensors are basically equivalent to NumPy arrays, but the main difference is that they can live on the CPU or GPU, whereas NumPy arrays can only live on the CPU. And so to interop between them, you can construct a torch tensor from a NumPy array with this from NumPy function. And if you want to convert a tensor to a NumPy array, the first thing you want to do is make sure it's on the CPU. So you call this CPU function, and you can call NumPy to get the NumPy array. And what's really nice about these tensors is that a single tensor can keep track of its own gradients. So if you add two tensors together, then multiply the result with another tensor, say. It can track all the gradients needed for chain rule so that, say, if you want to update the very first tensors in this graph, you can do that. So how do we create tensors? There's a lot of different ways. There's a PyTorch tutorial here. I'll send out these slides. It's called the PyTorch 60-minute blitz. They go into a lot more about this, but these are just some examples. So there's a torch.zeros function where you can pass in the width, height, and depth. You can create a tensor with the same shape as another tensor and the same device and data type with these underscore like methods. So for instance, one's like, zero's like. And you can also create a tensor and just pass in, you know, a nested list of values if you want. These are some of the ways to create tensors. And if we want to get information, we can get the dimensions with this size method. It's a little bit different from what NumPy does. I believe NumPy uses shape or something like that. And then we can also get the data type. So something like float 32 or int 32, whatever it is. We can also use device to see if it's a CPU or GPU tensor. So before I go on, this is like a lot of information. So I just want to say, like, hey, this workshop's going to move pretty fast. There's a lot of information that maybe slides in retrospect are not the best format for, but so if you have questions, let me know. And just remember that it's okay if like this stuff is not like, doesn't make immediate sense, like where it would be used or you know, because this slides, I'll send out these slides as a reference. There's the PyTorch documentation. It's mostly just so you have an idea of what all these capabilities are. So when you go to implement networks, you sort of know where to look for more information about how to do that. With that said, are there any questions so far? All right.
What is CUDA?
Yeah, so CUDA is basically, so NVIDIA GPUs are basically the industry standard for running deep learning. And CUDA is the, I guess, programming language for those GPUs. So it's basically, yeah, every now and then NVIDIA releases like a new version of this framework that basically is used to run things, to run general computes on a GPU. You use CUDA. And so PyTorch, when they say CUDA, they basically mean that we're putting this tensor on the GPU and manipulating it using this CUDA language. Does that answer your question?
Yeah.
Right. So now going on to how we can work with these tensors. So they're like NumPy arrays, right? So we can add them to do matrix multiplication. There's this thing called torch.matmul. And this is actually a pretty nice function just to know about because it works well with different shapes. So if you have like two vectors, it will give you the dot product. If you have some, like say, like a batch of tensors, it'll do the right thing there. This is a pretty versatile function. There's these interesting underscore operations you can use. I mean, a lot of this stuff is like, it can be useful at times. You don't need it, but it can be nice to know about. So basically, if you want to like say y equals y plus x, there's this add underscore function that will just modify y in place. And a lot of functions, if you just put an underscore after it, it will do that. To modify the device or data type, use this .to function. So you say like y.to device equals, say CUDA if you want to put it on the GPU, or CPU if you want to put it on the CPU. And this is nice because of what's a pretty common pattern that you'll see. We might have it in this notebook. Yeah, so you can basically just set this device variable at the beginning and say, like, okay, if I have you know access to a GPU, I'll use that. If I don't, I'll use a CPU. And then from then on, as long as you create all your tensors with that device, it will work properly. So it can be really nice just to simplify, right? Because if you just say like CUDA everywhere and your machine doesn't have a GPU, then you can't run anything. And that can be pretty annoying. All right. So remember that the main reason, apart from like faster computation on the GPU, the main reason that we used PyTorch was that it could do, you know, gradients, it could update weights for us. And so what they do is they create this graph under the hood. So if you like, you know, add two tensors, they create this hidden graph that says like, you know, these two are connected, and it stores the information. Now, this is really nice when we want to do training, when we want to update our weights. If we don't want to update our weights, we don't need any of this information. So especially if we're doing inference or we're testing our model, we don't need any of this information. And I'll get into how we work around that and tell PyTorch that we don't want to track this in a minute. But I just want to give a concrete example of how this graph works. And how this graph works is, so suppose we have right now just 1 by 1 tensors to keep things simple. So we have, say, y is equal to 5 times x. So I just write these lines, right? Python code, I say y equals 5 times x equals y plus 2. So the gradient of z with respect to y is just 1, right? Because if we increase y by some amount, z is increased by the same amount. Gradient of y with respect to x, though, is 5, right? Because if we add 1 to x, we add 5 to y. And so the gradient of z with respect to x, we can apply the chain rule, right? So x has an impact of 5 on y, y has an impact of 1 on z. We multiply them together. Gradient of z with respect to x is 5. So this is the sort of thing that we never have to do ourselves with PyTorch, because PyTorch will track all this automatically. Now, if we don't want to store this information, which can take a lot of memory, we can set, for a specific tensor, we can say requires grad equals false. We can run code with torch.noGrad, which will basically disable gradients in that code block. So it's pretty common to say, with torch.noGrad, and then you put your testing code. And then we can use, also if we want to detach, basically get a version of a tensor that's not in the graph, we can use detach. And if we want to make a true copy of a tensor, we can use detach clone. These are just some functions that, honestly, I haven't really worked with these two before, but they're definitely good to know about. And this PyTorch tutorial, I can go there for a second just to show you that it has like a lot of stuff about how to work with tensors. They go through some examples, creating like empty tensors, doing all sorts of operations. So if you want to go through this tutorial, they have a Colab, so you can just open it in Colab, work through it in your browser, download the Jupyter Notebook, whatever. So it's really nice if you want to get some more experience with tensors. So anyway, any questions about tensors?
I have a question. Now let's say we don't keep the computational graph like you're saying. How would it, if it wants to train itself again, how would it remember what gradients and what the layers were like and how to update everything according to chain rule?
Yeah. So if we don't keep the computational graph at test time, when we go to train it again, basically once we are outside of that torch.nograd, so once it's tracking things, we run the network once, get the output. From that, PyTorch knows what the computational graph is. So when we go to train time, we just run it, get our loss, and the graph is already back for us to use, if that makes sense. So that's sort of what's going on there. All right, by the way, if I'm going too fast, so there's in participants, there's like a go slower, go faster. So feel free to hit go slower. I know I tend to talk a little fast at times. So yeah, we have a decent amount of material to get through, maybe not too much, but a decent amount. So, all right, let's talk about, so there's this torch.nn. So this is super important. This is basically this documentation page. So PyTorch does this thing where they sort of put all their documentation into like these huge pages. And this torch.nn page has like a lot of the layers that you'll be using to build neural networks. So, we have layers like linear, right? We have nn.linear here. And the documentation will sort of tell us like, okay, it's applying this function. We pass in these input features and we pass in this shape, right? So when you're reading this, like this, they say n star h input. So here in this case, I believe n is the batch size, right? And then they sort of have, so a lot of times you'll want to get the shapes of tensors right. And this documentation can be really helpful in doing that. And they also give a code example, right, of how to use it. So in this case, they're making a linear layer 2030, and then they pass in, a tensor with batch size of 128, and these feature vectors of length 20, and they get the output, and it's of size 30, right? So this is just an example of the PyTorch documentation, which is super helpful. And really, as I said, like a lot of what I'm doing is just trying to give you guys some ideas of the stuff that you can look up in this documentation and figure out how to use in projects or in workbooks and notebooks, that sort of thing. So, linear, as I mentioned, you initialize with the input feature size, the output feature size. A lot of other network layers. There's dropout, which can be used to, as Joey mentioned, sort of prevent overfitting. There's conv2D, so convolutional neural networks are going to be the subject of another workshop, so I won't talk about them too much here. Same with LSTMs. But they're all here. They're all in this module. So for initializing weights, this is definitely not the best written slide. So what I'd say is PyTorch does initialize weights automatically. They have some default initialization that goes on. That said, oftentimes you'll want to initialize your weights. And there's this basically different initializers like Xavier uniform and normal. They're in this torch.nn.init. There's also this basically this Stack Overflow post sort of goes through basically how you create a function that initializes weights, and you basically use this net.apply. So you sort of apply this function, and what this function just does is it receives a module. It says, okay, if this is a linear module, I'm gonna apply this initializer, right? And so you can apply whatever you want. So as I said, like to some extent, this can be done automatically. It will sort of depend on your project team, right? What sort of initializer you need, but this is just something to be aware of. All right, so far we've talked about, layers, so like linear layers, but remember that, a big part of our neural networks was things like ReLU or tanh or sigmoid or activation functions. And what's interesting about activation functions is that though you use them to get your final output, they don't actually have any weights. So you don't have to actually store them as properties or variables of your class, of your module. And so there's this module called torch.nn.functional, which basically stores all of these sort of like activation functions, things that don't require weights. So dropout is also in functional, and ReLU is there too. So these you import, oftentimes you just import this module as F. You can create like, so basically what will happen is in forward, you'd say like, f.relu of whatever and call it that way. So again, the activation function slide shows up again. And then we have loss functions. So loss functions are in torch.nn. There's cross entropy loss, mean squared error, negative log likelihood, all sorts of stuff like this. There's also binary cross entropy. So there's a lot of loss functions. And yeah, there's not too much more to say about this slide. If you want to use a specific one, just look it up. The documentation will sort of have the signature. All right, so let's talk about optimizers. So in PyTorch, an optimizer is sort of the device that uses the loss function to update your weights. So it's basically, you can think of the optimizer as like the sort of machine that does gradient descent to update your weights. So there is a stochastic gradient descent optimizer. There's also Atom Optimizer, which uses sort of more advanced techniques that we won't talk about, but basically often delivers a better result in terms of updating the weights. But so it's sort of, you can just basically, you get all the parameters with net.parameters. So if you have some network, and these are all the trainable weights, and you pass those into the optimizer along with whatever learning rate or whatever else you want, and it will sort of do the optimization. So if we go here, there's sort of this example, right? So we have some model, we construct an SGD with the model.parameters, we set learning rate and momentum. So, so that's optimizers. And so sort of, how do we use an optimizer to actually update our network and sort of do all this stuff, right? So what we do is, this is probably, so, I feel like PyTorch is often pretty intuitive in that things sort of work the way you would expect, right? You have these Python classes. This is the part that's, to me, is probably one of the weird aspects of PyTorch, is that your optimizer, you have to manually zero the gradients every time you want to do a step of we train, we compute the loss, we backpropagate. You have to zero this gradient, because otherwise what will happen is if you compute the output you compute the loss on two different data points, it will just add those gradients together. And so it'll be you wanted to do an update on one, but you ended up doing an update on the last data point plus the gradient of the previous one and the previous one. So just remember to zero this at the beginning. So once you've zeroed it, you compute the output, right? You compute the loss, and then you call this thing called loss.backward. That will go back and do the backward pass, do the chain rule. And once you've done that, you update the weights with optimizer.step. Does this make sense to everyone? Does anyone have any questions about this, optimizers or anything that I've talked about previously?
What does net do again? It's basically
Yeah.
applying the thing, right? It's just passing the output in. I mean, input in.
Yeah, so we have some module, and when we call net of input, it will pass this input to the forward function and return to us the output of that function. PyTorch has a decent amount of magic like that, where things sort of happen a little different than you would expect just from like the Python, but it ends up making it easier to use. So
Wait, so what are the things that we were zeroing out? Like, why do we need optimizer.zero graph?
yeah, so basically, whenever we do loss.backward, it sort of just adds the gradients to the ones that were already there. So to make sure that we only get the gradient for the most recent output, we want to set it to 0 first and then do loss.backward.
Okay.
Because gradients basically they just keep adding up instead of yeah, basically, yeah, I think it might actually be we have to do it before this line. I'm not 100% sure, but it might be that this line sort of the gradients add and then our but yeah, that's a minor detail, but the main point is you want to keep just the gradients for the most recent data point. That's why you zero it. All right, so now we're sort of getting into talk about like so PyTorch sort of we just talked about sort of the core functionality of PyTorch. You know, it has everything you need to create a network, right? To run that network, to run it on the GPU, to do our different operations, our different layers, do our backpropagation, update our weights. But what's kind of nice is PyTorch also provides a lot of classes and a lot of modules to sort of make our life easier and make it easier to work with data, to do some of the common stuff that we do when we're training. So for instance, there's this Torch data set. So if we have some data set and we implement these get item and length methods. So basically we implement like array methods that you can sort of use it like an array. And we make it inherit from data set, then we can get a lot of functionality for free. We can use this data loader to shuffle the data, to put the data into batches. We can use data.random split to create our training and testing split. It's just really nice, right? Because writing like the same sort of batching, shuffling code, train and test code every time you want to train a network is like not that fun. It can be fun to do it the first couple of times. After a while, it's nice to just sort of have this data set that you can use. So just something to be aware of to make your life easier. Then we also have, so for saving and loading models. So this is actually, there's a couple of links I've put here. There's a tutorial and the documentation for this. And it's not too bad. So basically you just use this torch.save function, save your model, use torch.load to load it. You can also load this, basically there's this like state dictionary that sort of contains all the like parameters that get saved. So there's some stuff here. I would say the most important, so in terms of how to actually do this, like, you can look through the documentation, but the most important thing to be aware of here is that the structure of the save and load is based on all the like classes that you've defined. So if you change any of the names of your instance variables, I've run into this issue before. If you change any of the names of your instance variables, the old checkpoints will break because, like, for instance, if I had some layer called like linear 1 and I change it to like linear 0, 1, it will try to load linear 1. It'll say, well, this model doesn't have a variable named linear 1. And then it will say that doesn't work. So that's just something to be aware of, is that it's sort of based around the names of these instance variables. All right, so, and even outside of PyTorch itself, I just wanted to mention some nice libraries. So Torch Vision is really common. So if you want to do any kind of computer vision stuff, Torch Vision gives you basically really easy access to a lot of data sets, as well as a lot of models and a lot of transforms. So you can do like, random crops on your image or normalize your image. You can load a pre-trained ResNet and fine tune it pretty easily with this. You can even get data sets. So you can get MNIST, stuff like that. So for instance, for CFAR, we literally just initialize this data set. We specify the directory we want to download it to, whether we're training, if we want to put any transforms, and it'll just get the data for us. So it's really nice, right? If you just want to train a model on MNIST, you don't have to like manually download MNIST and set up like a bunch of code to process it. You can just use this Torch Vision. Similarly, if we want to get like just a generic model, like we just want to get ResNet, right? We can just load it like this. So it's pretty nice. It's nice to be aware of that. Torch Vision is there for that. There's also Torch Audio, which is for working with audio data. So I don't know if anyone's familiar with Librosa. Librosa is basically like the main Python library for working with audio. And Torch Vision is just kind of a wrapper for like common machine learning tasks. You want to load audio, convert it to some format. This will sort of depend on what project you're working with, but this can definitely be helpful as well. All right, last slide, I believe. So we're almost done. So first, I guess I'll stop for any questions. All right. This last slide is about getting GPUs for free. The slide is not super necessary now that everyone's set up their, has everyone set up their CSUA account?
Yeah, we should do that.
Cool. Yeah. So that's the main one. You know, 8 GPUs. Many of them are in use at various times, but you know, if you set up, basically one of the most important things about using CSUA is sort of just, there's this thing called CUDA visible devices. So like they only let you use a subset of the GPUs. And basically what I would say is like, you want to make sure that the GPUs you're using are not the same as what someone else is using, because otherwise like you won't, you might get like out of memory errors and stuff. So what you can do is you run this command called NVIDIA SMI. You see like, okay, you know, this GPU is at like most of its memories in use. I don't want to be using GPU 0, but like I want to be using GPU 1 and maybe GPU 7, right? Because those GPUs have very low memory usage. And also like this GPU usage is higher here and it's kind of low here. So, you know, then what we do is we set this environment variable, CUDA visible devices, to whatever we want to use. So this is just an aside. Like this is not super important to keep track of right now, but I just wanted to mention that, you know, with CSUA, making sure that you're using the GPUs that are free can be helpful. And a lot of times for a lot of tasks, as long as you can leave your computer open for a few hours, Google Colab can be really nice, right? Because you don't have to worry about like, is the GPU in use? You just spin up a Colab. You know, one of my projects, I sort of just left my computer running overnight to train again with Colab. So it's definitely great to have that option. But for longer running jobs, you want to run for a few days. You want to step away from your computer. CSUA is the way to go. All right. Whew. So that was a lot. Sorry if I talked too fast at the beginning. I tried to slow down a little bit. But yeah, hopefully that gave you some idea of all the different functionality in PyTorch. So let's get into now just going over what the notebook is going to be. So for the notebook, there's basically, we're going to start with some basic examples of like linear regression and logistic regression. So these are sort of to give you some experience working with tensors. So these sort of, we have these data and just sort of basically want you to create some tensors, create an optimizer, and just go through the whole process, right? Zero grad, compute the output. So in this case, you won't be using the network. For this first one, you'll just be manually doing the tensor operations yourself, right? So remember that you can sort of treat these like NumPy objects. You just do like, you know, add, multiply, stuff like that. And then basically get the, for testing, right, there's the no grad, and, you know, you get the predictions, convert them to a NumPy array, and then we'll plot them and sort of see like what it looks like. Similarly, the next part will be logistic regression. Sort of here you'll be creating a class, so you'll figure out, you know, what logic do I initialize as layers, what logic do I use functional for forward, creating optimizer, creating loss, going through the training loop, doing the no grad again, and seeing what the accuracy is. And the last part, so what I did was, this was like back in the summer, we were preparing these workshops. I was like, I wanted to find some data set that was kind of more interesting than the sort of like, you know, like there's a lot of like classical machine learning data sets, but I just wanted to find something, you know, a bit out of the way, like a bit different. So I learned about, there's this thing called the Riot League of Legends API, which gives you information about League of Legends games. So I went and downloaded some data. And what you're going to do is predict based on these stats who won the match, whether a player was on the winning team or losing team. So this is actually whether they won. So so basically what I've done here is created this match data set. This is a Torch data set, and you're going to have to implement, the get item and length methods. For that data set, you're going to have to use this random split function to create a train test split. And then you'll be able to create, a simple fully connected network, so linear network, and use it to train and see what kind of accuracy you can get. I was able to get pretty high accuracy. It got like 85%. I mean, and then it's sort of, this is like a bit contrived in that, if you know like the KDA and all the stats, it's pretty easy to tell who won. I'm sure, Kevin, you can probably attest to this. This is not maybe the hardest problem for a network. But yeah. And then at the end, I just put basically if you want to, yeah, they're all normalized. This is actually really important. So actually when I ran this and I didn't normalize the data, it actually wasn't working because some of the values were like really high. But like, once I normalized it, it actually worked pretty well. And then finally, just for fun, if you want to create your own requests, get your own data, I just put the code I used here. This is my token. My token expires in like 24 hours, so it expires pretty soon. But you can like create your own account there, get a token. They do this thing where they like rate limit you. So if you put too many requests in, then so basically this thing will just retry after a while. And you can get matches, get data. They have these JSON files, so it's pretty interesting if you want to play with that. But yeah, that's the main notebook. Any questions about this?
Pretty, do you play League?
Sorry? So I quit League because I was too bad at it.
No.
Yes. But yeah. All right, so any last questions before I send these to the Slack channel? Let me go ahead and send this workshop, this notebook. Wow, there is a 2 to 3 second delay between when I type in Slack and when it actually shows up. But here's that, and then I'll send the slides as well. So let me know if you have any issues accessing the slides in the Colab, if I need to update the sharing permissions or something like that. Yeah, I should
can't
just make sure.
Collab.
Let's see. The sharing for the PyTorch is, oh, it is not shared. There we go. Okay. So PyTorch notebook should be working now. And the slides should also be visible. Oh, why is there a cat running across the screen? Yeah, so this is actually, oh yeah, I forgot to give everyone an introduction to Google Colab. So a quick show of hands, yes or no in the participants tab. Who has used Google Colab before? Oh, so everyone's used it. Okay, so you all know about Google Colab. You know that it's like Jupyter in the cloud and how to update. Okay, you know how to use the runtime type for GPU, TPU. Now, what you probably don't know about is the hidden superpower of Google Colab is if you go to, where is it?
I think it's help settings and then other or something like that.
Yes, settings. So there's this miscellaneous. So there's a power level, and there's corgi mode and kitty mode. And if you have power level, it's really great because if you code, oh wait, I don't have screen share up. My bad. Let me put the screen share up. Sorry, this is really. Go ahead and get started on the notebook. Let me know if you have any questions. In the meantime, this is what happens when you set the. So Google Colab has some fun features. They have this this like combo tracker for how many keys you type and stuff like that. Anyway, I guess I should probably stop. I can probably leave the recording running for now for the next couple minutes. Do we usually complete the workshops during the session, or do you usually work on them after?
Yeah, for last week we did it like at home, and then we just had to finish by the
Did it
next
when?
Sunday. We did it by ourselves last time.
Okay. Yeah, so I'll probably just stop the recording then.